Hello everyone. Our next topic for the A-level chemistry is from group 17 halogens, the reactions of halogens with hydrogen. As we have discussed in our previous lecture that reactivity from top to bottom, from fluorine to iodine, reactivity of the halogen decreases. When we react hydrogen with fluorine, explosive reaction takes place because fluorine is the most reactive element of a halogen group, and this reaction takes place even in a darkness at a very low temperature. Explosive reaction takes place which is difficult to control. When hydrogen reacts with chlorine in the presence of sunlight, its reaction takes place violently or vigorously and HCl gas is formed. HCl gas is formed. But when hydrogen reacts with bromine, because bromine is already present in the liquid state and is less reactive, so on heating this reaction takes place. On heating this reaction takes place. And with iodine, even on heating, it produces an equilibrium mixture. In all the above reactions, normally we can represent also with the reversible sign, but as the thermal stability of HF is maximum, that's why we represent this reaction with the single-headed arrow. Similarly, whenever hydrogen and chlorine reacts, produce HCl. Now, the reverse reaction only takes place in a closed system. If the system is not closed, then we can also represent this reaction with single-headed arrow, means reactant will change into the product, but product will not easily change into the reactants. Similarly, in case of reaction with hydrogen and bromine, the reaction can be also represented by single-headed arrow. Why this is? Because the thermal stability of all these halogen acids decreases from top to bottom. Thermal stability decreases. It means that HI can easily be decomposed on heating. That's why whenever hydrogen reacts with iodine, then on heating it reacts but form an equilibrium mixtures. This means that the produced hydrogen iodide immediately start decomposing and converts back into hydrogen and iodine. But in case of all these HBr, HCl and HF, as HF is the maximum thermally stable, that's why once this will form, it will not be decomposed quite easily into hydrogen and fluorine. That's why all these reactions can be represented by a single-headed arrow. And in case of iodine, as the HI decompose immediately, start decomposing, that's why an equilibrium mixture will be produced at the similar conditions of temperature and pressure as the other halogens are going to react. Next is the thermal stability. As we know that from top to bottom, size of halogen atom is increasing. So what will happen? Automatically, due to size increasing, but due to the large electronegativity difference. In case of HF, we have the electronegativity of hydrogen 2.1, but of fluorine is 4. 4 minus 2.1 is equal to 1.9. It means that there will be a maximum electronegativity difference between hydrogen and fluorine, producing maximum polarity, or rather we can say ionic character, into the molecule which supply it the extra force of attraction between the charges. That's why its bond energy is 562 kilojoule per mole. The maximum energy is, bond energy is for HF. The bond energy of HCl is 431 kilojoule per mole. It means that now the electronegativity difference is decreased. If we consider the electronegativity of chlorine is 3.5 minus 2.1, what is the difference? The difference is 1.4. It means that the electronegativity difference decrease, polarity decrease, charges decrease, force of attraction decrease. That's why lesser amount of energy is required to decompose the molecule of HCl. So the bond energy decreased to 431. In a similar manner, from top to bottom, the bond energy of HBr is 366 and of HI is 299. Why? Because the electronegativity in case of hydrogen iodide becomes least, because the electronegativity of iodine is 2.8, electronegativity of hydrogen is 2.1. What is the difference? The difference is only 0.7, and it is just about the non-polar character. That's why the polarity is minimum, force of attraction is minimum. That's why the bond energy is minimum. That's why the thermal stability from top to bottom decreases. Mean more easily decomposed is Hi, then HBr, then HCl, and the maximum thermally stable or least decomposes HF. The reason is, again, bond length and percentage ionic character or polar character is there, which makes the thermal stability decrease from top to bottom. Now, next are the reactions of halide. Reactions of halide, and these reactions are used in chemistry as a chemical test for halide. For example, if we have different types of halide, say chloride, bromide, or iodide, these are the iodide, these are the halide ion. We use silver nitrate as a reagent for the identification, followed by the addition of few drops of dilute HNO3 to destroy all the carbonates or other substances which can produce white precipitate that can mislead the students. Now, if we will react immediately, a precipitate will form of AgCl, and this will form in the solid state, producing nitrate ion separate. Nitrate ion separate. If we add AgNO3 into bromide ion, this will produce silver bromide, AgBr plus nitrate ion. And similarly, if we add AgNO3 into iodide ion, we will get silver iodide plus nitrate ion. Now, the color of AgCl will be white. White precipitate, PPT, will form. White precipitate will form, and in case of bromide ion, cream colored precipitate will form, and in case of silver iodide, pale yellow precipitate will form. Now, to confirm these precipitate, either these are of halides, then again confirmatory test is used. What we do, we add first dilute ammonia solution. On adding dilute ammonia solution, this precipitate, white precipitate of silver chloride will dissolve, but the precipitate of silver bromide and silver iodide will remains as such, mean remains insoluble. Again, for the reconfirmation, if we add concentrated ammonia solution. If we add concentrated ammonia solution, then both of these, silver chloride and silver bromide precipitates, that will be dissolved, and only the silver iodide precipitate will remain insoluble. In this manner, we can judge, we can bifurcate or distinguish between these precipitates, and the respective halide can be detected quite easily. In this manner, these halide react and the halogen reacts with hydrogen, producing different types of halogen acids. Now, the acidic nature of halogen acids are discussed as halogen acids are HF, HCl, HBr and HI, as this is the thermally less stable and this is the maximum stable. If we want to judge the acidic character of all these halogen acids, then we can say this is a weak acid and this is a strongest acid. Why? Because due to the hydrogen bonding, percentage ionization of HF molecule will not take place in aqueous solution. That's why, due to the study of hydrogen ion into the molecule with hydrogen bonding, percentage ionization will decrease. But in case of HI, the percentage ionization will be increased too much because the iodide ion is larger and hydrogen is away from the nucleus. That's why bond length will be increased and bond will easily be broken. So HI will be ionized more as compared to HF. That's why the acidic strength from top to bottom increases. Similarly, if we compare all these halide, their nature, then we can say that iodide ion is the strongest reducing agent than bromide ion. Bromide ion is stronger reducing agent than chloride ion, and chloride ion is stronger reducing agent than fluoride ion. Means the electron removal from the iodide ion due to the larger size, it is quite easy. That's why iodide ion can easily be changed into iodine atom by using electron. Definitely this will act as a reducing agent, and this property decreases from iodide to fluoride ion. It means that their reducing nature decreases. I have explained all the consent properties of halide ion and halogens. Hope you understood all these concepts. Please comment, like, share and subscribe our YouTube channel for the upcoming valuable video lectures. Thank you all.